and you can think about it, it's not hard to sort of remember which one they're missing. Um, and all right, so that's kind of clear. So in other words, so thinking about that, you know that, so let me remind you of all the coefficients. So we have alpha, beta, I'll put rho and sigma kind of go together, beta bar, alpha bar. And signatures of these are -2, -1, 0, 1, 2. Yes. Okay. All right. And basically, and just remind you, so these ones all satisfy have a nabla 3 and a nabla 4 equation. Nabla 3, nabla 4, nabla 3, nabla 4. And these extremal ones are missing a pair. They only have one. So this one only has a nabla 3 equation. This one only has a nabla 4 equation. Right? And so just immediately from there, and then again, so we also know that each nabla 3 equation basically takes the following form. You have your whichever, well, I'll write it schematically. So you have nabla 3 of some curvature component, and that will equal, there's some angular operator. I'll just write it, again, I'm being schematic, like this, right? And then all of the nonlinear terms all take the form Ricci coefficient times curvature. All right. So, okay. And then nabla 4 will be the same. Okay, so now, all right, so so basically, so things that satisfy nabla 3 are everything but alpha bar. So I can consider this, so everything will satisfy an equation of this form except for alpha bar. And so it's reasonable to think that, again, in the same way that we got for little omega and eta bar, we were able to get this estimate relatively easily. It's reasonable to think that we would get this estimate easily for these ones, right? We just have to make sure that, well, first of all, we're gonna have to commute this equation a bunch of times. We'll have to use the commutation formula. Then we just have to make sure that the stuff here is in the bootstrap norm, right? Is controlled by the bootstrap norm. But that's not, well, there's sort of only one thing really to check in a way, which is, all right, so let's just think schematically. So let me just go over here. All right, so let's go ahead and even commute this equation. So we're gonna have to commute it for j up to n minus 1. And so we're gonna have nabla 3. So I apply the covariant derivative on the sphere, j times to it. I have this, and then on the right-hand side, so then I'm gonna get its commutator. Yeah, I should say there's also, yeah, there are all these things, but remember, there's also this Gauss curvature floating around. Maybe I'll say something in a second. And well, Gauss curvature, we throw into these, if you remember in the norm. So Gauss curvature basically is treated like one of these ones. It has a flux in both directions, and it has this one. We'll get to that one sort of later. Yeah, but for now, I'm not looking at Gauss curvature now, because well, it turns out that you can show that Gauss curvature actually satisfies a type of one of these Bianchi type things, but I'm not going to use that structure right now. So for now, maybe it's, sorry, this is an aside, but if you remember, Gauss curvature satisfies some equation, which is roughly of the form, there's a rho, it's basically rho plus something like this, right? That's all. That's the only thing that we'll use later. This equation is called the Gauss equation, because it comes from the, you're looking at the Gauss, you have the sphere, you have your sphere sitting in your 4-dimensional space-time. Using the Gauss and Cadazzi equations can relate various things. The Gauss equation becomes this on the sphere. The Gauss equation relates the curvature of the sphere to the ambient ones, and it's a sphere, so curvature is all just the Gauss curvature. And anyway, when you do the linear algebra, it becomes this. Okay. Great. All right, so we have this, and then we have plus this, and then over here you get all that crap over here. Okay. So now we just have to look at this, and I want to argue quickly. Again, I'm not going to formally introduce all the notation to write this out. I'll sort of just say it. Um, all right, well, let's look at this term here. So the point is, okay, so we are applying up to n minus one terms. So here we're going to have, so this thing will involve up to n angular derivatives. All right. Um, and remember that I said that because of this, the first estimate we did for the metric coefficients, geometric Sobolev norms on the spheres, in other words, Sobolev norms involving these G slash derivatives are the same as the, like we don't have to, it can go back and forth between controlling this is the same as controlling like the coordinate, spherical coordinate derivatives, right? Okay, and so basically we just need to make sure, so we're going to integrate this in the three direction. So we just have to make sure that this is something, because not all curvature components are controllable in the three direction, right? So we just have to make sure that this is not the bad one, right? Um, and did anyone see why? Did that already? So first of all, what's the one we want to avoid? What's the bad one? So what's the one that we don't control a flux integrated in U? Alpha. Yeah, it's true that alpha bar is going to be the enemy, and that alpha bar we'll see that it's sort of the scarier one in some sense. But but yeah, it's because it's the opposite. Because think when you do the energy estimate, like so this is like so replace nabla 3 for now with du. So this one you have du of alpha. So you're going to do when you integrate this over space-time, you integrate in u, and then you get boundary terms on oh, sorry, I mean u is this way. So you integrate in u, so you get these boundary terms. So that's so you get a V flux. So this one is missing the U flux. We'll see that a V flux is kind of better. Well, eventually we'll see. Well, we sort of saw that already when we did the nonlinear wave equations. We saw that it was kind of, if you control those fluxes, that was useful for getting some. It's like this is the analog of dV of the wave equation, which was good. But it's anyway, it's still it's sort of this thing. I mean, in general, it's good, but it's also true that you're missing a flux, which could mess you up. However, you can argue with signature considerations that this term, the doesn't the bad term doesn't happen. Is that a
So alpha is missing the B flux. Alpha bar is missing.
no, the other way around? Alpha is missing the U flux. Alpha bar is missing the V flux. So in other words, the natural fluxes for alpha are integrals along U equals constant. These are the natural fluxes that you get for alpha for different U. And the natural fluxes for these are integrals along V equals constant. Is that correct? Yeah. All right, with angular derivatives. And I'm just making the point that it's sort of, in general, this is a much better thing to control. I mean, one way to see that is because the integral on a V equals constant is a very small interval. And so that's kind of, I mean, you might think that this sort of should just be small naturally because it's a small integral, but somehow, I mean, when you do, it doesn't automatically small. So it's like somehow here you can take advantage. This doesn't use up your smallness in the definition. So in general, this is better, except if like you still, but it's still annoying that you don't have the other one. And also note it's only sort of really relevant at the highest amount of derivatives because even if you were one derivative lower, then you can use that alpha satisfies this. So it's just that because we're commuting up to n minus one times, it's possible that you really get n derivatives here. For anything less, then even if you saw alpha, it would be fine because then you could just use this to control the integral in U. Okay, but it's important for the scheme. Well, actually, I don't. Yeah, I guess certainly important for the scheme as I'm presenting it that we really control in the soup norm up to here. Um, I suspect that it's not. I think you actually don't need it, but anyway. Okay. So, but now finally, what's the signature thing? So we claim. So I claim. So this cannot be alpha. So why? Well, signature. So, all right. So alpha has signature. So signature of alpha is -2. Nabla 3, um, Nabla 3 does what? Nabla 3 raises the signature by 1. So so if Nabla 3 like equaled some angular derivative of alpha, this would have to have signature -3, but no such term exists. Again, this is an extremely silly argument because you can just look at the equations and see that there's no such. You can see that alpha shows up on the right-hand side with an angular derivative exactly only in nabla 4 of beta equals divergence of alpha. But anyway, if you know, don't have your computer open, you could just do that. All right, so we're good. So basically, now this puts us in more or less the same situation as the as we had with the Ricci coefficient. So in other words, um, and again, maybe I could sort of say it in words. I mean, so we're going to do the same thing. You're going to multiply this equation by nabla j of this, write this as derivative of the norm squared, integrate on the sphere, pull it out. Then over here, you can, I mean, the point is, again, if, you distribute all these derivatives, and if the maximal number of derivatives, so here, if you get slash n of psi, then you're gonna, you'll control that in your L2. Well, it's exactly like we did with the Ricci coefficient. I mean, you start with um, it's I don't know, should I write it out? I mean, it was just this estimate. I'm just saying. So you have like it's roughly something like this. You have du equals some h, and I'm just saying this is the scalar version. I'm just going to remind you quickly. So you have 1/2 du equals f times h, right? And then you integrate this, and so you get like the sup over u and -1 to -1 plus epsilon of well, you integrate over the square of f squared is less than, you get some data term, right, from f at zero, from f at u equals -1, and then you get plus this integral. You have integral over the spheres and the integral from -1 to -1 plus epsilon of this against f du. And now, of course, now the mistake, you don't, do AMGM here because you want to apply Cauchy-Schwarz to you want to put this in L1 and do Cauchy-Schwarz to pick up the epsilon. So, but that's fine. So what you do is you pull this out in L infinity. You use that well, and you could even just use the bootstrap. You don't need to even. So this term, you just say this term is less than the sup in u of f, and then you do Cauchy-Schwarz and you pick up an epsilon. So times epsilon, what would it just be epsilon? This is the 1/2, I think. What?
We had this left.
With the 1/2. But anything that I write on a given day could be wrong. So just because I wrote something before, but we had this discussion even. Okay. Anyway, right. So anyway, that's the key. So you use like that kind of inequality. And then, okay, and applying the analog of this up here, these would all be bootstrapped. So you don't, in fact, you could sort of play some game where you try to absorb it over here, but you don't even forget that. I mean, well, because I mean, there are other terms where more generally this f might not be that f. But the point is, once you have an epsilon, you just everything, then you're like home free because everything is just bootstrap and then you're good. All right, anyway, so you do that same thing here. Again, if to be careful, you need to really expand this out. In general, right, every time you do this commutation, you could get curvature, for example, right? You could pick up a beta bar times this, and then you get more angular derivatives, and you have to play the game. So there are two curvature components. You might get a little worried, right, with this game because it's important when you have this game that one of them you can soup. But again, it's the same principle. I'm going to take like a billion derivatives, and it's impossible, only one of them can have all the derivatives, and the other one will be much lower, and so I'll be able to use this one. Again, it's very important if you're actually interested in working the subject that you know how to write that formally. But I'm going to skip it because I'll just write something wrong probably. All right, questions?
So this last formula that you put said that the two f's on the right hand side and the left hand side can be different.
I'm just saying you want it. Well, no, not here. I mean, I'm just saying before. I should. You could throw on. I'm just saying you know, buy something like that. It's just that it would work. Well, the other thing is like, well, for example, when you do, it's also that this is also kind of a linear version of it. You could imagine. So, for example, when you start commuting here, when you commute, you pick up like you get things that are very nonlinear. And so it's not, in other words, like when you do this commutation, you could then see a term like Ricci coefficient times this. And then like you could have that, and then you could take another angular derivative. Well, anyway, I'm just saying, then you have something cubic. And then so it's like it could be when you run through the same thing, this thing comes out and the power is like not the right power to absorb over there. So it just doesn't make, but it's all bootstrappable and you have the epsilon. Again, very good exercise to actually work that out. Any questions on the chat? No? Cool. All right. So that's that. All right. So the upshot. So the upshot is that we control, well, I'll just say that we have the soup. So everything that satisfies an alpha 3 equation. So which is alpha, beta, rho, sigma, beta bar, we control in hn minus 1 squared. Okay, that's nice. It's nice because that was sort of in some sense easy. Uh, but it still doesn't help us over here because you see this place where we got stuck here. Well, it could help us with some lower amount of derivatives, but it doesn't help like because it's some we want to these things we want to be able to control n angular derivatives of these Ricci coefficients, right? And so we have to commute this n times, and then we're going to hit this n times, and so it's n. It's not n anyways. We'll have in principle to do n, not n minus 1. And so before we can fully resolve this part where we got stuck, we're going to need to actually have we'll need to have close some energy. We'll need the high norm, in other words. We can't just do everything with the low norm, which is not surprising, of course, because otherwise the low norm can't close because it loses derivatives. There'll always be this issue if you try to just use the low norm. All right, makes sense. Okay, so now we have to stop and we have to ask ourselves, um, well, we have to sort of, yeah, think about how our energy estimate, like how we're going to control the energy estimates. And again, we did this model equation already, um, where we've really seen sort of the key point. So let me quickly remind you. So recall for the nonlinear wave, we had this, what was the deal? So we had all these commutations. So I'm just going to write the terms on the like there are all these the good things on the left hand side, and there's some stuff on the right hand side we have to control. So roughly, so we would have some integral over the whole rectangle, right? And then you would have some, well, you had like dv. There's some number of derivatives on. So you had some number of derivatives on this times some number of derivatives on that. Maybe I don't know. Let's just be very schematic, something squared like this. Anyway, the key point that allowed us to close was that one of these things, in particular this dv one, because you had these integrals in the this one you controlled on for u equals constant. You had the integrals and u equals constant, and so so again you have this integral over this whole rectangle. This one you control over each of these, so you could take the soup out of those, and then what remained was an integral this way, where there was an epsilon, and then you close. Okay, so I'm being very schematic. Of course, we had to argue there's something, the more derivatives were here or there or whatever, but that's like very, very high level. This was the point, is that our structural condition on the nonlinearity told us that, I mean, because we couldn't see a term with all du. So if it's all du, then that's like that's really bad. Because then you could get you have to control something like this with just du everywhere, and then there would be no way to get smallness. But the point was that the specific structure of the nonlinearity said that doesn't happen. So you always have a term which has this flux, and then you win. All right, so now what's the analog? I mean, it's kind of not that mysterious what the analog is here, right? So again, we have this structure that some things have u fluxes, some things have v fluxes. So now we just have to ask ourselves, is it the case like I have to look at the space-time term that I get when I do the energy estimate, and if there's something there that has a v flux, I'm good, basically. It's sort of as simple as that. Um, and I can even, well, I could even do something a little. I can be sort of slightly more sophisticated and than the estimate I did there. So if you remember, probably don't remember, but the way I phrased the estimate with the wave equations was that so you have box, right? Maybe this was commuted a bunch equals, and there's some nonlinear term. This was commuted a bunch. We multiplied this by either du or dv, right? And then what I did is I just applied Cauchy-Schwarz and and didn't just focus on the squared. But I don't have to. I can I can reserve the right to when I do my or my AMGM or whatever you want to call it. I can reserve the right to like put a small constant somewhere. So I'm gonna when I analyze this system, I'm going to not just immediately split it. I'm going to leave it because I want to remember. It could be that maybe this one of these terms is good even though this one isn't, or all right, so I guess I don't need to erase that. Okay, so now let's so with that being said, so let's consider, so what sort of are the nonlinear terms one needs to control in the energy estimates? All right, well, okay, so let's look schematically. So we're at a given Bianchi pair will be of this form, right? Will be Nabla 3 of one of them. You have some angular operator applied to the second one. Then you have these, and then you have Nabla 4, this. Then you have minus the adjoint of whatever that angular thing is applied to this one, right? Okay, that's the form of the equation, right? Schematic form. So then okay, of course we have to commute. Right, so again, so now we let J go from all the way up to N now. And again, I'm not going to say much about the terms from the commutator, but I don't want to really pretend. I don't want to just straight up pretend they're not there. Right. Okay, and then we get some terms. So then we'll have, right, uh, you have this. You also have then yeah, plus. Okay, that's the first one. Note that this commutator here is where Gauss curvature is going to show up, right? Because this is a commutator of all things intrinsic to the sphere. So that gives you some curvature. So that's why it's you want to have well, I mean, yeah, either you want to make sure you have K in your bootstrap assumptions. Of course, you can sort of just, I mean, you can always just anytime K shows up, just use that equation to sub rho plus those Ricci coefficients. But anyway, one way or another, there's some Gauss curvature there. And then you have a similar thing with this. Minus. All right. All right. Now I'm gonna focus on these terms here. All the terms, the stuff that's generated from the commutators is all dealt with similarly. Okay. All right. And so now what do we do? We multiply, right? So this one we multiply, well, not really multiply, again, it's a tensor. We contract with this using G slash. It's the same way I did those transport equations, right? But I sort of wrote it out in more detail um, last lecture. All right, we're going to contract this one with that, and this one will contract with this, right? All right, and then basically you do that global integration by parts. Then you effectively integrate over then you integrate over the rectangle, integrate over the rectangle. Again, well, you don't, I say integrate over the rectangle. In reality, you integrate over every possible subrectangle, right? Because you want all the different fluxes. So remember if here is right, so here's in principle our rectangle. But you want to you do this estimate in every subrectangle, you're going to do the estimate because you want to get, all possible sort of fluxes. Okay. So you do it in every subrectangle, and the upshot. All right, and then the upshot is that you get all right, so you'll have a soup over, so for the one with the nobla 3, you're going to get the soup over u equals constant. So you get the soup over u equals constant of this plus the soup over v equals constant this is one of that, right? And then of course you see your data term. All right, there's stuff with the commutators. I'm going to ignore that because it's really treated the same. And then what I want to focus on is this other term. So we're going to see here um, nobla j of psi times psi times of this. So this is a generic psi. And then here we might see this, or we might see this. We added the two estimates together, right? Okay. And so now this is the thing we have to question, when can we control it? And basically, the idea is one way you can definitely control this term, and you don't even have to think about the structure of this yet, is if one of these equations, if psi1 or psi2 is something that you control a u equals constant flux on, then you're good. So here's the claim. So, and I'll justify in a second. So claim. So if in the bootstrap, well, let me say it even more concretely. So if psi1 and psi2 are both not equal to alpha bar, then you're good. Then this term is controllable. And briefly, why is that? It's just for because we're going to be able to use the same kind of structure here. So so I have some big expression like this. If as long as neither of these are alpha bar, in other words, the Bianchi pair that I'm looking at, as long as the Bianchi pair that I'm looking at is not the final one, is not beta bar alpha bar. So if it's any of the other ones, then then these things will not involve alpha bar because it only shows up in the final one. And and then all the ones that aren't alpha bar all have those V fluxes. So in other words, if I have some space-time norm, okay, other than I have to make sure the nonlinear things work out. We'll say something in a second about that. Um, but let's like suppose I did some AMGM. I put square here, like square here for a second. These things squared, I have these are integrated over the rectangle. But again, because of this fact, I control that flux. I can pull them out the bootstrap and gain an epsilon. All right. Um, all right. But you say, what about this term? But this is where I was saying I'm going to be ever so slightly more sophisticated than the estimate I did there. Because of course, if I can get an epsilon here, then I have some wiggle room, right? I could put an epsilon, like when I do the AMGM, I could throw an epsilon to the 1/2 here, put an epsilon to the minus 1/2 here, and then when I get the epsilon, I win, right? So in reality, if these are okay, these are okay. Again, just assuming I just have to make sure that, I can do the I still need to have enough derivatives to play that game on the Sobolev to do the game with the Sobolev norms, right? But we've seen that now quite a few times. Okay, so upshot. So what I do is I say so why? So I'll write this and then we'll take our break. So why? Well, so first of all, I just say, okay, so because this is less than epsilon to the 1/2 times this, right? Right? Okay, this one will just be fine because why? Well, there are all sorts of ways to see it, but this J can be at most N, right? And well, I mean, you just play the game, right? So you write this as again, so you can write this as you can consider separately the following situations. Um, uh, you break it up like that, and you consider one case where so either J1, say, is less than N over 2, or J2 is less than N over 2, right? Um, Again, that's just from the product rule, the derivative, right? Okay, and then so for example, so if J1 is less than N over 2, then you say, all right, so let me introduce, well, let me now throw in, let me write this integral of V over U, integral of V, I've been suppressing that there's an integral over a sphere, right? So we have the sphere of, so we have this term. Like I just need to argue that, so note this term has an epsilon here, so I just need to argue I can control with the bootstrap. I mean, I could almost just tell you that this is the same. We've already sort of seen this, but just for completeness, right? So then because this one is small, I'm going to take that term out in L infinity. So I say the integral of U, integral of V of the soup over the soup here, right? I could do that. And then I apply the Sobolev inequality, right? And so I have integral over U V of integral over S UV of and I just have to add two derivatives. Right. And then now this is controlled because J1 is quite small. J1 is like less than n over 2. So when I add 2 to it, I certainly have that n over 2 plus 2 is less than n because n is huge. And so this thing is controlled by the Ricci coefficient norm. So in soup, in soup. So this thing, this integral is just bounded by the bootstrap, I call that P, I guess, right? And then I just have a space-time term for this. But no matter what C is, I either control the integrals on U or the integrals on V, one of them. And so this whole thing is controlled by bootstrap. And there's an epsilon. So that's good in that case. Then there's also then you have to consider the case. There's a similar case when J2 is less than n over 2, but you just do the same thing, except that so if J2, if this is the small one, then at this step you pull out the curvature in the soup, and well, then you can just argue the same. Right. You have to pull the soup out, the one that has less derivatives, because you're going to then add two to it. And you have to make sure that when you add two, it's still less than, not too high. Okay. So that's good. So that tells us that this term is good. So um, this term is good. And then this term, is even simpler. So again, because these are all terms that are controlled in the v equals constant, these are all less than epsilon to the minus 1/2, some bootstrap times the integral from -1 to -1 plus epsilon, which is epsilon. So that works too. All right. Um, so that's nice. So this, all right, so then we'll soon take our break. So the upshot of all of that is that we control the basically all of all the um well, let me say it correctly. So I have so this means that I can do the Bianchi estimates for alpha beta. I can do it for beta rho sigma, and I can do it for rho sigma and beta bar. But I'm missing alpha bar and beta bar. And then from these, I can think about which fluxes that ends up giving me. And so for alpha, so I'll have the integral over u equals constant of alpha squared in Hn. Well, let me not, these Hns are always with respect to the sphere. I guess we can remember that. So I have this, then I have, all right, then I also have, well, beta, I have both, so I don't have to think about it. So I have beta, or let me just write all the ones so then I have beta, rho and sigma, also I have both, so these are good. All right, and then now beta bar in principle, in the bootstrap norm, beta bar shows up. I have both fluxes, but I wasn't able to, this argument only works for these ones. So I have to think about what's the flux I get for this one. And if you think about it, this one and here beta bar comes with so this one is of the form nabla 3 of rho sigma and nabla 4 of beta bar. So, I mean, if to think about that, this one starts nabla 3, nabla 4, then this is nabla 3, nabla 4, nabla 3, nabla 4. And so then there's always the confusion. So this means that I control this is exactly also this vehicle's, this U equals constant one. No, no, not the small one, right? Oh, no, 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 you're right. I always mess this up. I don't know what my problem is. All right. Yeah. So I don't control it here. And so what I control is this one. All right. So these are now closed. This is what I have so far. All right. Which is not everything, but it's something. In particular, after we take our break, what we'll see is that this is now enough to go back to the missing Ricci coefficients. And do some other, it's not going to be just this, but this plus some type of nonlinear analysis that we already did with the jet computations will be enough to close the Ricci coefficients. All right, so let's take a 10-minute break. So let's reconvene at 4:15, say. All right, so let's carry on. Okay, so let's go back to these to the Ricci coefficients now. I don't know what board did I maybe that one. Okay, so let's go there. All right, so So now we're going to use a few things. Okay, well, first, we're going to go in two steps. So, all right, so what we've done before, so let's recall. So we have these ones are totally good, right? So, and then for chi hat and trace chi, um, uh, um, wait, what am I? Oh, I guess I didn't write them before, but I mean, there were more that were good here, right? So also trace chi bar is good and chi hat bar are also good, right? Those also all satisfy. For some reason, I just wrote these ones, but trace chi bar and chi hat bar also satisfy novel three equations. They don't have they there's just curve. Well, anyway, all the same. I argued in such a schematic way that the reason it also works for those. It's just that I didn't write them. Um, the only you just need to know that these satisfy novel three equations and they don't couple. The novel three equations for these quantities does not couple to an angular derivative of Ricci coefficient, right? Um, because these ones, novel three of these had that issue. So the analog here is novel four of these, but we're using novel three, so that's good. All right, so these ones are all fine by what I said before. All right, these ones are almost fine. So we have up to n minus one is good, right? And then so far we don't what we're missing completely. Um, so eta and omega bar. And of course, we're also missing completely torsion, but I'm not going to write torsion because torsion can just be recovered. But but torsion, is like a suitable sum of it just is equal to one half eta plus eta bar. And so I can just like eliminate torsion everywhere. I can just replace torsion with eta plus eta bar. All right, so it's really these ones, completely missing these. Okay, so it makes sense at this stage to break it into two pieces. So first we're going to talk about doing up to n minus one derivatives of these, and then once we have the n minus one, then we'll sort of consider these all together. All right. Um, okay, and now this n minus one part, this is really like the formal, like we did with the whatchamacallit, the formal jet computation. So the formal jet computation, remember, we went by like it was almost like I didn't phrase it as an induction argument, but because only three signatures, but it's basically like some kind of induction. This is like an inductive procedure. We started with the signature minus one, and then you worked your way up. Uh, and so in this case, and so basically we have all of the signature minus one or omega chi hat bar this we have up to n minus one. So okay, so let's focus on up to n minus one derivatives. All right. So in that inductive step, so the next step in that formal jet computation was to do signature zero, right? And it's important that we split it up like that. So you don't want to do. I mean, okay, well, let's just one step at a time. All right, and so the only signature 0, 1 that we're missing is eta, right? And so eta will satisfy some equation like this, right? Okay, so now and then in fact, um, we have to commute too. So you might even think we should look at so for now, J is in up to minus one. Okay, so now we do our usual signature again. All right, so eta signature zero. Nabla four lowers you by one. So this has to be signature minus one. which means it's what?
You say that again.
I'm saying so eta, signature of eta is 0. So therefore the signature of nabla 4 of eta is -1. So this one, because nabla 4 lowers, because remember signature is 3s minus 4s. So this one has to be -1. So well, I mean, so this means it has to be beta. Exactly. All right. And that's good because remember the reason we got stuck before because I said, all right, one way or another, we're going to integrate this, and I need to have some like um and there's no way to get smallness here, so I need to already control this. But oh, I didn't write. Sorry. I forgot to write. Remember, at this last step, I also already have all these ones that appear twice. I have all of them. So I also have beta, rho, and sigma. That's important. Okay. And so beta is here. And that, see, this is a fortunate, this structurally worked out well because beta is exactly, I have actually both fluxes of beta, but in particular, I have integrals on u equals constant of beta, right? Which is exactly the kind of thing that would show up if I integrate in the four direction, I get exactly the integral on u equals constant. And that's something that I already control in terms of data. So that's great. That means potentially I'm in business, right? Okay, but there's still this issue that I sort of don't have smallness, right? Okay, so this one I don't need to worry about getting smallness because it's sort of good to go. Um, so that's nice. So we control this. All right, what about these ones? These nonlinear terms. All right, these ones, okay, well, let's just think about what they have to be. So again, the signature of this has to be -1. And then remember the signature, all Ricci coefficients, signature can only be like -1, 0, or 1. So you have to think of how can things add up to -1 if it's -1, 0, or 1. But we said all these same words before when we did the formal jet thing, if you remember. And the only possibility, right, is that it's a -1 thing and a 0 thing, right? So therefore, um, so this implies that this is actually something of the form like -1 times 0. So what, and again, what something very explicit that this signature consideration rules out is that you cannot see nabla 4 of eta equals eta squared. That's the bad thing. That's the kind of ODE which might blow up. If you see derivative of a quantity equals that same thing squared, then that's scary. That's like what you see in Raichaduri. And Raichaduri does blow up sometimes. That's the singularity theorem, right? But this, remember, this whole theorem we're doing is assuming that you have a solution to Raichaduri to begin with, right? But this one cannot do that kind of Raichaduri blow up because of this calculation. All right. Okay. Now we have to think, how are we going to exploit that? Well, the point is that, all right, these sigma -1s, we already have for up to, we already control up to n-1 derivatives of these. Meaning that these are less than data again, something depending on data. All right. So the idea is, okay, so I'm going to do some estimate here and then integrate this. I mean, it still looks a little weird. But now we can play that game with the exponential weight. Before we did it with the energy estimate, but now I can play that game with the same game with the transport equation. So um, let me write out for like a scalar, forgetting about the tensorial structure, let me write out how that works, and then it will be clear. I should say, or you can think you apply ground rules inequality. But I prefer to think with exponential weights. I like to keep things basic. Even Gronwall is like too sophisticated for me. But I like the exponential weight is really simple. All right, anyway, the point is just here's the schematic. So the schematic is you have an equation like this, right? Equals say h times f, and you know that you control this is already controlled. And I want to say that I can get some estimate for f here. So again, you can just literally apply Grandwall. But what I want to do with the exponential estimates is I'm going to say the following. So of course I can write df equals 2, right, h f squared, right, by multiplying by f on both sides. And now I do the same game with the weights. So I'm going to Um, Multiply both sides with e to the minus AV, e to the minus um, AV, right? And we do this thing. So then we have dV. This is basically the same game that I did with the energy estimates. So boom, boom, and then assuming I got my signs right, you get this. Okay. And now the point is, if A is large enough, depending just on the constant D, right? Because we know that H is controlled by data. So I can pick, so if I basically now when I integrate this, like from v equals 0 up to whatever v, this term comes with a good sign. It's on the left-hand side of my estimate. This is something bad. But because this is just something is bounded, I can pick A so big that I can absorb this into here. And the key thing, this largeness of A doesn't depend on some, because I already know this, it doesn't depend on like a bootstrap assumption, bootstrap argument. It just is some, it grows, but it's some, it can, and again, and ultimately what I get, it says that F's sort of like F squared kind of is bounded after I multiply by an exponential weight, which is of course the same thing as saying F can grow at some exponential rate. But I control that exponential rate, A, by data. So it's fine. All right. Um, and basically we can just do the exact same thing up there. Right. Just, now, okay, if it's not scalar, they're the tensors, integrate over the sphere, do all that crap like I already talked about. All right, we can play this game, play the same game. Again, the key reason it works is because of this fact that because of the signature considerations, these nonlinear terms involve something we already have estimated times something that we're estimating. So remember sigma zero here, sigma zero, if it's signature zero, it means I can write it as some combination of eta and eta bar. If it's eta bar, I've already estimated it. So, right. And so the only other option is eta, which I am estimating. So it really is, really is the model problem. All right. Okay. And so, all right, then of course, yeah. So this beta, I've also already estimated in those flux storms. So that's fine. When I integrate, that's fine. There are these ones, again, I won't write it out explicitly just for the sake of time, but just schematically, we know again, well, there's some curvature that can show up when you do this commutation. But again, the curvature now before with eta, it's going to give you uh so now before lowers by one, the curvature component that shows up with one commutation is again has to be beta just by signature consideration. So beta was already fine here. So it's anyway, kind of it works out for the same structural reasons. Okay, so the upshot, again, I'm being informal. I'm not writing all the details. You should check if you are interested in really understanding these things. But the upshot is that we have this now. Right? And again, so you're gonna take those equations, multiply with nalpla j of eta, integrate on the sphere, do the fundamental theorem of calculus in the v direction, and use all this stuff. Well, and multiply with the weight, exponential weight, and do all that stuff. All right, questions? Zoom has been very quiet today. All right, cool. Okay, so now let's go to, so having done the eta one, now we go to omega bar. And omega bar, um, what's the point there? So omega bar is a quantity now is a quantity of signature one, right? So okay, so omega bar is signature one. All right, so let's look. So what does that tell us about this equation? It tells us that um Well, it tells us that this term has to be signature 0, which means it has to be either rho or sigma. In fact, if you look at the equations, it's rho. It doesn't, but at any rate, again, we don't really care because this is nice. Again, exactly rho or sigma are things that we already totally control. We control any flux of those. So that's good. Um, and then again, you have to go to these guys. All right, so we know that the signature of this is equal to 1. So now you have to, oh, sorry, 0. Yeah, yeah, sorry, just spaced out.
0, 0, or -1.
Exactly. Yeah. So we have two possibilities. We can have -1, we got 1 and -1, or 0, 0. All right. And now, so note here that if we had sort of considered all together the eta with the omega bar equation instead of doing this like kind of inductive structure like we did with the jet computation, you would be very worried here because this looks like this is like a quadratic combination. Anyway, I already made this point when we did the jet stuff, but this is fine now because we already estimated all sigma 0 terms. So this is just known. We know this, at least up to n-1. But that's what we're doing right now. So that's fine. We can take all the derivatives we want of that. It's just data. Like forget about it. And then this one, this kind of term, how has the exact same structure of this term? That is to say, it's it's something that we are because we've also the other notice the other -1 things are so the other signature equals 1 things are trace chi bar and chi-hat bar, but we have those. So so you're good. So either you have something. So in the psi ones we also control up to n-1 at least. So either we already control those and we control that, or it's exactly something we know times the thing we're estimating, i.e., it's like a linear equation. It's just the same structure, and so you can argue the same. All right, that it really is the same. Okay, so all right, so upshot, we control soup over uv. All right, great. So now we've controlled all Ricci coefficients up to n-1 derivatives. But now we need to do, so we need to do the HN norm for, and now it seems a little harder at first. So, and in fact, it's possible that this all looks a bit strange because, why did I spend all this time arguing that the n-1 was fine? You would think what's different doing n, right? Um, because these ones now I don't, right? I don't have, we haven't done already. So now I need to do these ones and I need to do eta and I need to do eta bar. And now it's things look a little, well, disturbing from various points of view. Um, various points of view. Okay, because well, certainly our whole scheme for doing these ones was conditional on like you had to go through this inductive process, right, to already control these. All right, so we have to control these, but these ones we know are not good equation. I mean, this Nabla 4, right? The whole point, we can't use Nabla 3 of this because of the regularity problem at the higher level derivatives because of this angular derivative eta. So we're stuck with trace chi, but that's Raichaduri, right? Right? We know this has trace chi squared, blah, 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 right? And I mean, you can see, so again, this is signature -1. This is nabla 4 on that. It's -2. So you can see -1, -1. This is allowed, and moreover, it happens. This is bad. Okay. Um, so what's does anyone know the resolution? So the point is we already know n-1, right? We're just doing n. So of course this would be a problem if I didn't already know something, because this could blow up. But the point is, it's this is principle fundamental to nonlinear PDE that nonlinear when you differentiate nonlinearities, they become like more and more linear in the highest derivative. So so if I differentiate this a million times, so I only have to worry, I really have to just do n at this point, right? Okay, so there's some commutator term. We'll think about that in a second, maybe. Well, or I'll just continue with, I just tell you the commutator works the same. I kind of like that. Give you some homework. All right, so what happens if nabla n hits this? Well, and there's of course other stuff. Well, um, well, I mean, it's clear. You do the product rule. This will be, all right, so the only terms we don't already know are nabla n of trace chi. So it's clear that, I mean, either all of the n derivatives can hit the first one or all of the n derivatives can hit the second one. Right, so okay, that's one possibility, is that you have this. And then it's plus something known, right? Because I already know n up to n-1. But now this is linear, and this quantity, which is what we're estimating, this is a linear equation in that quantity because we already control this because of the n-1 stuff. This is a key structure. So again, this is related to this fact about well-posedness for nonlinear equations that I mentioned, that once sort of there's some critical norm often if you control things that's at some finite level of regularity, that once you control it, all higher regularity automatically propagates. It's because of a similar thing. So once you know, like for a nonlinear wave equation dimension 3, like once it's something like, if you control the solution L infinity or derivative in L infinity, then in reality you could propagate h 5 million. And it's because of this thing that you inductively just take a lot of derivatives, and as long as, okay, to get the L infinity statement you have to work a little hard, but you take a bunch of derivatives, and you know like as long as you have this thing is under control, there's something that you need to get started. But once you have some sufficient amount under control, as you take derivatives, you just get inductively, you just keep solving linear equations. And so linear things don't blow up the same way. All right, anyway, it's the same. This is the structure here. All right, but let's think a little more about, but we have to be a little careful because it's not just trace chi on the other side, right? And in fact, in fact, all of these, all of these terms are showing up. So, right, there's also, on the right-hand side of this equation, I mean, in principle, you can see, right, it's like this is signature, like we just said, -2. So you know that it's not just that you can see these terms, you have to see. These are the only possible nonlinear terms. They're all bad ones. So you can see, you can see something like this, and you do see it. There's also chi hat squared. You do see that. All right. So all those terms, the upshot is they're all going to be, so now let's switch. Let's write this a little more schematically. So more schematically, we're going to get nabla n of this, and then I'm going to write it like nabla n of some psi -1 times some psi -1, because that's the thing that we don't know, plus, known stuff. You can play the same game with the commutator. I mean, if you think it's just, again, this nabla n can only hit one thing at most, basically. So it's sort of the same structure happens. Um, all right, so you have this. But this doesn't close by itself, because even if I do the weight, because I can see like they're also the omega bar and the chi hat and all those things, right? But that's fine, because basically I can go through all of these equations and I can play the same game. So, what's the point is that now as long as like it's sort of back to like when we were doing the first transport equation structures that that when we did those Nobel 3 equations, that it wasn't really because of how they worked, because there was a smallness and that and integrating in the epsilon, we didn't need to analyze the specific form of the nonlinear interaction wasn't that important. So it's similarly here, because we've differentiated the equation a lot and we're working at a high enough regularity, the you know, the equations have become linear. And so the specific nonlinear structure of the term is sort of not that important. You sort of just need to check that everything is in like in your boots, that you can control the thing. I.e., you need to make sure more concretely, and it's something we've already, well, with one caveat, you need to make sure that, for example, when you see things like this, you have controlled it. But I've already checked, right? We've already done this check that in the all right, so let's look at all right, so let me now make this all more precise. All right, so for trace chi bar, we have this. So Ricciarduri doesn't have a curvature term on the right-hand side, actually. Um, so I'm even going to write it like this. I'm going to write it like, so what we could see here, we could see trace chi, we could see chi hat, just to make it very kind of clear what's going on here. Or we could see, uh, no, we could see omega. Oh, but omega we control. Oh, I wrote omega bar there. That was wrong. Sorry, it's omega because omega has signature -1, right? Omega bar has signature 1. Anyway, we see this. This term is actually not that scary because we already control omega at the highest level. Okay, so somehow, so the upshot is that the equation looks like this. This is sort of the schematic times, and I'm just going to put like, big O of D because it's times something that we can control in point basically in any slope level norm we'd want to do. It's going to be, well, in L infinity is controlled in by the data, and then plus also like no. Again, I'm being just sort of for the sake of time and just keep things clear. I'm being very schematic. A lot of terms here, right? But the point is everything, if the full number derivatives don't fall on this thing, then you have slightly less than n everywhere, and it's all stuff we've already controlled. Okay. All right, so that's that. Now what about the chi-hat equation? Um, okay. Well, so one option, now the most naive thing would be maybe to use the Nobel-Forov chi-hat equation. This one, it takes this form. This is actually a bad equation to use. Why? Because here there is a curvature term. And again, so we know that this is signature -2. So this thing has to be um, alpha. Oh wait, is that bad? Maybe that's not bad. Oh, I guess that's fine, actually. Okay, it would be fine actually. For some reason, I kind of usually the more traditional way to do this is also to use the yeah, I think here that would be fine because we control alpha and we've already closed it in its energy estimate. So that's actually not a problem. All right, but there's also this other equation, Kadazi, which is often used in conjunction with this one, and it takes the form. So it has this divergence of chi hat. I wanted to use this equation because we discussed all these operators on the spheres and their elliptic properties. So just so that we use the things we learned. All right, so you could use this one, but let's use this one instead. So this one takes the form divergence of chi hat equals, and again, principle to curvature. You have the term angular derivative of this, and then you have some nonlinear things like this. Now, again, by signature, this is signature minus 1. This is an angular thing, so this thing has to be beta. This has to be a minus 1, right? Okay, and what's nice about this is you can, well, this equation, a nice thing about it is you can use, we use those elliptic estimates. So basically, this will say that I can control this, right? It said the divergence acting on symmetric trace-free tensors is elliptic. So in other words, I can control, like, well, n derivatives of this is controlled by this and n minus 1 derivatives on the sphere, right? And so we'll be able to square everything. Um, well, and then this is the same thing. So this has to be signature. So this is signature minus 1. So again, the way you can get the signature, so if you have minus 1, 0, and 1, there are not many ways to get minus 1. This has to be something minus 1 times something um, uh, times something 0. Oh, actually, I guess I want to use this other. Sorry. I want to use the structure. I need to differentiate this a bunch and then use it. It becomes linear, this thing again. All right, so I can commute this, say, with n minus 1 times here. And then here I'm going to get n of trace chi. And then again, I'm going to get, right, this nabla n derivatives. If anything less than n, I already control every possible norm here. So the only thing I'm worried about is if all n derivatives hit one of these things. So basically, so that's now I could get nabla n of chi hat, trace chi, or eta, um, again, times something like, I'll write it like this. Okay, and then I can use the elliptic estimate to say that so this thing controls hn, um, is less than all of this crap in L2. Okay, and again, the key structure is because it's this thing. This looked like some scary nonlinear term. Do I have to analyze it? Well, not so much now because I just take a bunch of angular derivatives and it just becomes linear in all the things. Okay, so what this is useful for example, when I go and I estimate this here, and if I see this term in L2, I can just pass from this term. I can go ahead and throw, just replace it with, with these terms in principle. But actually, now that I don't think I like that because I want to gain my epsilon to the AV. Sorry, so I don't know. I wanted to do this, but I think actually this one would be better to do. Because right, I want to use the structure that I used here, right? Where I put an e to the AV and I do this derivative and then gain something large. But if but this equation doesn't allow me. Oh, sorry. I know what it is. Sorry. It's because here, these are all, I apply n minus 1 to this, right? So I don't even get this. Sorry. I apply n minus 1. And so here is only n minus 1. It's because this is elliptic. It's n minus 1 times this. So this is all just already known. Sorry, I just confused myself. Sorry for that. Right. So again, so the equation is of this form. This is an elliptic operator. It gains a derivative on the right-hand side. So if I want to control n total derivative, I only have to compute n minus 1 times. All right. So all of these ones then are just fine in any norm. So the only bad one is this, which is n derivative trace chi. But that's something that I'm going to be estimating here. And I'm going to do that trick with the exponential weight. And I'm going to gain something large. So I'm not scared of that. And then this term is a curvature. So that's fine. Okay. So sorry about that. You can also use this one and differentiate it a bunch. Okay, so now, okay, we're really running out of time. But basically, you play the now you can play the same game and all the other ones. Play the same game with eta and um, and eta bar. So just for the sake of time, I'll because I really want to get start next lecture with the applying all of this stuff to self-similar to the topic of the name of the course. It's good to have at least 3 lectures to do that. You can play the same game there. I mean, the upshot is again, you differentiate things many times, everything basically becomes linear, and then linear equations. So then you just sort of have a set of linear transport equations. You can either think you apply ground wall, or you can be very pedestrian and just in all these novel four equations, throw in these exponential weights and it ends up working. Okay, so then basically, the upshot is this, is that all Ricci coefficients are done. Okay. And then also from that, we get that, so K is also done. Because the Gauss curvature is equal to rho, is basically rho plus some Ricci coefficients. In rho, we control both fluxes for rho are done. I mean, I didn't even say it explicitly, but we've already alpha, beta, rho, and sigma. We already control every possible thing that because we got all. I mean, there's only one flux that's even possible for this, but we do control it. And these ones we control all the possible fluxes already, and we already did all of the low norms except for alpha bar. So, all right, so that's good. So we have all the Ricci coefficients and almost done with all the curvature. So all that kind of remains is only one thing you even can do, which is to try to do the energy estimate for alpha bar and beta bar at this point. Um, but again, it kind of has to work at this point. Why? Because, well, just give me one sec. All right, so only remains to well to do. I mean, only remain. I mean, we have. So we're missing again. We're missing one flux bound for beta bar, and we're missing like all of the estimates for alpha bar. But so let's see. So next, so the like natural remaining equation is the beta bar alpha bar the Yaki pair. We haven't even used. Well, I guess we use this equation to get the low norm for alpha bar, but we haven't even touched this at the energy estimate level, and we need to do that. And all right, so what will this look like? This looks like nabla 3 of beta bar equals some angular derivative alpha bar, in fact, the divergence, plus things that are of this form. And then here we have nabla 4 of alpha bar equals some minus the adjoint of that acting on beta bar plus also these. All right. But now basically you're kind of good to go. Because why? Because it's kind of why those things were good to go. Because now we've already all of these guys we control. So because we've closed the estimates for all the Ricci coefficients. Which means that this is basically a linear equation. Right? So all these, you can estimate these by data. And therefore, well, when you do your estimates, okay, so first of all, when we do the energy estimate here, so these ones are all going to get multiplied, you know. So just running out of time. So the right-hand sides here, you're going to see, so let's call this, we call this AH1 and this H2, right? So, okay, we're going to take a bunch of derivatives, right? So you're going to see, so there are a bunch of derivatives of H1 times beta bar, and then you can get a bunch of derivatives times H2 times alpha bar. All right, this one, first of all, is fine for the same reason that all of the original energy estimates were fine, because beta bar is something that you control, you're going to control a flux and the U equals constant flux. So so it's really this one that you could be worried about. But everything here is secretly linear. So I mean, somehow, so first of all, I mean, you simply already control the only thing that you could like not have an estimate for here that can show up is something that involved alpha bar again. Because we control, when you estimate these, so we have in these terms. So if something involves, if the curvature term in here is not alpha bar, you're good by the same reason. So the only thing you're worried about is alpha bar. There are terms like that because there's some term, for example, there's a term in here that involves trace chi alpha bar. All right, so the only thing that you could be worried about is nabla j of some this times alpha bar, and then it's this is times alpha j of alpha bar. This is the only kind of thing that you could be worried about. But again, this you already control in whatever norm you want, basically. And so at the end of the day, this is like just something depending on data, and then you have a space-time norm involving some angular derivatives of alpha bar. You do Sobolev, whatever, all that stuff. All right, okay. But then this is exactly the kind of thing that you can eat with the exponential weight. Because again, the thing multiplying this, it's bounded by data. You have a quantitative bound for it. So as long as over here, before you did this whole process, you threw in this e to the minus AV, then over here you will generate over here some term like this. And now you just have to pick this A to be large depending on the data and everything. And you win and you're done. That's wow. Sorry, so I sped up a little bit at the end, but I think I really covered the main points. And at any rate, given the structure of this course, of course, it's not that important that it's not about that you need to reproduce this proof or whatever. I'm trying to give an aspect of the flavor of the kind of like how you do analysis double null gauge. And I think this is basically even though it's not super simple, it's like the simplest setting possible where you can see this kind of this type of nonlinear analysis, structural analysis, is behind basically everything in the subject, one way or another. And it also shows the basic kind of estimates you can do. Okay, so that closes the bootstrap, and like I said, that's what I'm going to. So I'll consider the characteristic initial value problem to now have been established. Okay, so finally, we're ready to do what sort of was the main goal of the course, which is, so remember, so there was this first part of the course I talked about, well, the very first part, I did all this cosmic censorship stuff. All right, fine. Then I talked about these Christodoulou things, these self-similar solutions. And then I said, what I want to do is I want to develop sort of techniques to construct analogs of Christodoulou solutions for the Einstein vacuum equation. So now basically, and the key techniques are exactly double null gauge characteristic initial value problem. And so what I'm going to explain on Wednesday is kind of a way to do that, basically, a strategy, which I mean, the point is, and then just in 1 minute, I mean, what's the point? I mean, so you can try to impose directly some self-similarity on the vacuum equations, and you could try to do it like we did with Christodoulou. There are various issues. I mean, the main one is just that there's just so many equations. I mean, spherical symmetry is already pretty complicated, right? But there's not that many equations of spherical symmetry, and so it's just a huge mess if you try to do it directly for the vacuum equations. And so I'm going to describe a sort of some kind of a trick which uses very much this characteristic initial value problem, where you can reduce by some kind of trick, you can kind of reduce things to, well, certain formal jet computations and then certain a priori estimates to construct them. And so I'll describe how that allows you to construct some analogs of the scale invariant solutions. And then hopefully by the end of the course, I mean, I'll only be able to do the briefest of sketches. I'll describe also how you can do some analogs of the naked singularities, which will be another level of sophistication. All right, so I'll stop there, or I'll answer any questions.